If you've ever tried to silence a noisy room, your first instinct was probably to staple egg crate foam or fiberglass panels directly to the drywall. It feels like a thick, soft layer should absorb the noise and keep the room quiet, but a classic acoustic experiment proves otherwise. Imagine a loud electric buzzer sitting on a table in the open. A sound level meter placed nearby reads a steady baseline of 70 decibels. Watch the meter as we cover the buzzer with a porous glass fiber box. The sound level drops by a measly 3 decibels. The noise cuts right through. Swap that glass fiber for dense plywood and the noise plummets by a massive 28 decibels. Why does a thin layer of hardwood successfully block the noise, while a much thicker box of dense fiberglass lets the sound pass through as if it's barely there? Acoustic control hinges on a microscopic interaction between mass and friction. To block noise, we first have to understand how it travels. Sound moves through the air as a longitudinal pressure wave. At a microscopic level, air molecules crowd together and bump their neighbors, overshooting their resting place due to inertia. But the air's natural elasticity acts like a spring, snapping particles back. They do a tiny, vibrating dance, passing kinetic energy down the line. Sound is a chain reaction of kinetic energy passing through a medium. If we can interrupt that chain, we can kill the noise. Let's see what happens at the exact moment this chain reaction of air molecules crashes into a dense solid boundary, like concrete or thick glass. Zooming into the solid wall, we see its tightly packed, dense atomic lattice. When lightweight, agitated air particles slam against these massive solid molecules, there's an extreme mismatch in momentum. The air particles lack the force to push the heavy wall, resulting in an inefficient transfer of kinetic energy. Governed by the mass law, the heavier the wall, the higher its molecular inertia, resisting vibration. Faced with this immense inertia, the wall acts like an acoustic mirror. The vast majority of the sound wave's energy is violently reflected backwards into the room. A minuscule fraction of that kinetic energy does manage to vibrate the solid structure, leaking a faint amount of noise through to the other side. Dense solids use sheer mass to stubbornly reject acoustic energy and bounce it away. Now, let's swap that solid glass for glass wool. This material is made of the exact same heavy silicates, but spun into a fluffy, lightweight web. The rigid barrier is gone. Instead, we swoop down to find a microscopic, cavernous maze filled with millions of tiny open pores. Because the material is porous, the wave penetrates deep inside. The air molecules are forced to physically rub against the tiny glass strands. This mechanical rubbing creates friction, actively robbing the wave's kinetic energy and converting it into unnoticeable heat. Porous materials trap the wave's energy and assassinate it through a labyrinth of friction. Applying this molecular perspective to our buzzer experiment reveals exactly why the results were so lopsided. The glass wool box failed to block the noise because its open pores completely lack the structural inertia needed to stop a pressure wave. It let the sound bleed right through. The plywood box succeeded because its dense molecular structure possessed the mass required to reflect the wave back toward the buzzer. But that solid plywood box has a critical flaw. By reflecting the sound inward, it traps the acoustic energy. The reverberant noise level inside the box itself actually increases. To fix this, we look to the ultimate architectural solution. A cutaway reveals a hybrid wall design. We place a heavy, high-inertia solid on the exterior and a porous, friction-generating material on the interior. As a sound wave hits the wall, the heavy solid layer blocks external noise from escaping. At the same time, the porous layer destroys the internal sound reflections before they can bounce back into the room. True acoustic control requires manipulating 2 core laws of physics, using massive inertia to build an impenetrable boundary, and microscopic friction to shape the silence within.